Hello, everyone. So I'm Gabriel. I'm a postdoc in KTH. And today I'm going to present work mainly performed by Tao Tu and supervised by Peter Edstrom at KTH in partnership with the Engineering Institute of Aeronautical and Materials and with experience performed at ILL in France. Sorry. Then on additive melting by wire arc additively manufactured 17.4 pH stainless steel. So for a short introduction of the material, this 17.4 pH stainless steel have wide range of applications due to this relatively high mechanical strength, hardness, and ductility, keeping a good corrosion resistance. These mechanical properties are mainly due to their microstructure, of course, and with the phase hardening with the martensitic structure and precipitation hardening coming from copper nanoprecipitates. And those are tunable by mechanical properties, and especially in conventional process through the precipitation hardening. Another interesting properties of these materials that they are good weldability, which makes them good candidate for additive manufacturing. And if we take a look at the number of papers, so here I plot the ratio between published paper and paper, the overall paper in engineering materials field. Otherwise, all the number of paper are increasing. So you see that for pH steel and additive manufacturing, you have an increase of published paper. And if we split down into different techniques, then you have a majority of work focusing on SLM, also have work on EBM and one coming after yachts here. And we choose then this study focus on this topic. Why then? Because this process have some interests. It have allowed to achieve relatively high deposition rates. Cost for materials and equipment are relatively low compared to other processes, and it also allowed to build medium to large scale parts. However, it's not really suitable for small or very high complex parts, and the surface roughness is not always so good. Here you can see on this picture that just has built material have a quite high surface roughness and would need machining for probably most of the industrial application. However, just as printed, the mechanical properties of this 17.4 pH is relatively poor in terms of yield strength and hardness. So the question we had is how to enhance those properties through thermal treatments, as we saw before, through the tuning of the microstructure with thermal treatments. So here I just put the materials. So it's 17.4 pH because 17 chromium, 4 nickels, more or less. Here you have high copper composition for precipitation of these nanophase copper precipitates. And our methodology was to apply different thermal treatments, starting from the as-built, so aging at 480 up to 4 hours, or dual thermal treatment with first solution treatment at high temperature with different temperature and time, and subsequent quench, and then subsequent aging at 480 for up to 4 hours. And all this will be then compared in terms of microstructure, characterized in terms of microstructure and mechanical properties for highness tensile tests. And microstructure is also compared to thermodynamic simulation that have been done, but I'm not gonna present so much this on this presentation. So first of all, let's take a look at the as-built condition. So you see as printed, you have a kind of columnar structure. This is the building direction is on the vertical direction. You have some cell inside. You can see that at the boundaries of this cell, you have chromium segregation. You have some precipitates as well. In terms of crystallographic microstructure, you have a quite high crystallographic texture. This is EBSD imaging for inverse pole figure and phase mapping. And then you have also dual phase material with FCC, austenite, and BCC, which can be martensite or delta ferrite. And can say that this FCC is more the soft and ductile phase, where this BCC is more hard and less ductile. And then you have at the end something like 30% of FCC. And what can be put forward is that we have quite a non-homogeneous chemical microstructure in terms of chemical composition and features, which probably leads to these poor mechanical properties that we'll see after. Yeah. So one strategy is to apply this solution treatment. Solution treatment will have effect to homogenize the microstructure. So we pass on the austenization and then we quench. So here is the as-built microstructure for record. And then we have the microstructure after the solution treatment and quench. So here you see that we reduce a lot the amount of FCC austenite phases. We also have much less texture, even though we keep some texture. Here is the phase mapping. And then you see we apply different solution treatment at different temperature up to 1200 degrees C, 2 hours. And for all of this, we have more or less the same 4% FCC. While for 1200 degrees C at 15 hours, so very long solution treatment, we have a little bit reduced against this FCC value. So question now is what's happened during the subsequent aging. So we will show here on this slide aging performed after 2 hours, and we'll see just after that why I pick up this 2 hours aging. So from the as-built materials, there's mostly not much happening in terms of phase transformation. However, if we see the solid treated alloys, then after aging of this 1040 degrees C, half an hour, we have an increase of the FCC phase to 18% at the end of the term of the aging, 2 hour aging at 480. And it's decreasing with the solution treatment, 10% for those two. And for the last one, we have 5% of FCC after aging. So that this austenite reversion, so this metastable alpha BCC phases transforming to FCC is reducing with the solution treatment, which means that we have more homogenized microstructure after higher solution treatment, which is expected, right? But what is really interesting is that then with this process, we can tune the amount of FCC. We have the soft phases, and then we can tune the amount of the ratio between soft and hard phases that we will have on our materials, and then likely tune the mechanical properties, which is not possible in conventional process because we don't start from this very heterogeneous microstructure. So in terms of hardness evolution, here I plot the hardness of all our solution treatment alloys as well as the as-built stage over the aging time. So here is the as-quench material or as-built, and after following aging, right? Yeah. So we see that first we have quite a strong increase of the hardness at the first stage of the aging, which is very likely due to the precipitation hardening, so the precipitation of this nano precipitate of copper, and because this BCC, FCC would only have softening effect, right? Transformation. At the very end, we have a lowering of the hardness, which could be meaning that the precipitation hardening is not optimal anymore, or also we have some the phase hardening decreasing. And we have more or less a peak hardening, so optimal precipitation and phase hardening after 2 hours of aging. This is why I showed you the 2 hours aging before. And also global trend is that with the solution treatment, we have increased the global hardness, the overall hardness over the aging time, which is in line with the decrease of FCC phase. And so we can tune the hardness depending on the FCC amount. So now we're gonna talk about the nano copper precipitation. And to investigate this nano precipitate of copper, we used small angle neutron scattering, in situ small angle neutron scattering. So we'll briefly introduce the technique, very briefly. So since of small angle neutron scattering, the idea is to have a neutron source. It was ELL, so it was nuclear reactor at the beamline D33, pass through the sample and scattered with the precipitates. And then it will give us a 2D scattering pattern. This pattern, so it was done in situ. So we have a furnace at 480 degrees C. And then we could measure every 10 minutes, one frame every 10 minutes. With this pattern, we do azimuthal integration, and then we get a 1D curve. So in intensity, the experimental intensity are the blue dots. Here, the dots next to the left side are the intensity close to the center of the detector, while the dots on the right are the intensity on the edge. And here you see that we have different contribution on this curve, different scattering, what's so-called porous scattering, which in this case will be caused to coarse precipitates or porosity or whatever in your materials. It's this green line here. We have an incoherent background, which is constant contribution. And we have this nano precipitate contribution, which made this kind of bulge, which is the one who's interesting the most, right? So let's see how this contribution moves with the aging time. So here I put the two extreme material, the as-built material and the solid treatment material at the highest temperature time. And you see that here you have the scattering pattern after 10 minutes, 2 hours, up to 3.5 hours. Right? And you see that finally both curves are relatively similar, which means that the precipitation are relatively similar. Starting point have very few copper precipitates, which also explain why the hardness is so low. And we still have a few precipitates. We can model them here, actually, even if it's not obvious by eyes, and we can also see it by TEM. And here, with the time, you see the copper precipitation increasing with this precipitates contribution increasing. Here, from this curve, you can do model fitting and then extract the mean diameter of precipitates for the as-built and solution treatment. You see how it's evolved, and you can also extract the integrated intensity, which will be very short related to volume fraction of your precipitates. And you see that it's increasing and reach a kind of plateau. And after 2 hours, we basically have nucleate and growth. Certainly most of the copper precipitate, which explain why we have this peak hardening at 2 hours. And then after that, we have certainly coarsening, mostly coarsening of the copper precipitates. And so which could explain that after the mechanical properties could decrease, because if they're becoming bigger and less in density, that's not the best. So what about other precipitates? We also have a few other precipitates, of course. We have some chromium carbides. So here I display a lot of data from Soleil cyclotron on the FABS beamline. So it's XRD data, wide-angle X-ray scattering for all the different alloy, different solution treatment, and different aging time. So a lot of data, but in short, what we see that we have some chromium carbides in low volume fraction. We have some inclusion, MNS, MnSeO3, and we also have, more interestingly, some niobium carbonitride, which are present only in these stages, these two stages. So they are precipitates at high temperature, but at too high temperature, 1200, they are dissolving. So then we cannot see them anymore. And after aging, they do not reprecipitate. It's not high enough temperature. Okay, so now I'm gonna present finally the mechanical strengths, the mechanical properties in terms of tensile strengths. So we compare those data to a rough 17.4 pH, which will be your conventional process reference. It's in yellow, purple. And we have so in the as-built, we see that it's much below in terms of yield strengths and etc. But if we apply this aging, then we increase the yield strength, also the elongation to rupture, or the ductility. Interestingly, for these three alloys, we have very similar tensile test results, even through the FCC fraction vary from 30 to 10%. Of course, a bit surprising. And for this final highest temperature alloy solution treatment, then we have very high yield strength, so high, similar to the rough material, and relatively high, maybe even a bit better ductility. What is interesting here is also that we could tune then through this process the mechanical properties, depending if you want high yield strength and lower ductility, or lower yield strength and higher ductility of your alloy, which is possible thanks to this additive manufacturing process. So in conclusion, we see that the influence of solution treatment plus aging on phase fraction, also on precipitation of copper precipitates with a 2-hour aging, which is the peak hardening for this alloy at 480. The potential to tune the properties and the mechanical properties in terms of hardness, and also maybe later intense tensile behavior through the phase hardening and FCC contents. One perspective of the work would be to understand why this variation from 30 to 10% FCC do not seem to change much the tensile properties of these three alloys, which could also be linked to secondary precipitates like this NBCN that we found only on those alloy and not on this one, for instance, or other factor that we didn't acknowledge yet. So that's it. Thank you for your attention. And if you have any question, I would be happy to.